Okay, so here's what we were talking about last time, this idea of surface independence. We just barely got into this ever so slightly, so let me remind you of what the idea is. Recall we have this idea of path independence. Path independence says, this is a feature of a vector field. Some vector fields have this remarkable characteristic that as long as two curves that start at the same point and end at the same point, the line integral is going to be the same. Right, no matter what. And this seems super weird right up until the point where you think about, what about gradient fields? Right? If that's the gradient of some function, well, then of course these integrals are equal. Both of these are f of b minus f of a. And by assumption, these two curves have the same b and they have the same a. So, so these integrals really ought to be equal. Right? Okay. Right. So, and then I've asserted but not proved that not only is every gradient path independent, but every path independent field, regularity ignored, every path independent field is also a gradient. Okay. All right. So the analogous idea, going to the diagram. and I forgot to open that up. Oh well. But here's our diagram in R3. Taking this notion of, look, if a field has the property that any two curves with the same boundary points, that the line integral is always going to give you the same value. If you just take that concept as it is represented on the diagram and just shift up by one dimension, the idea would be, if the pattern holds, that there may be some fields that have the feature that any two surfaces that have the same boundary curve may have the feature that the fluxes through those two surfaces are always the same. Right? So in the same way that path independence is a feature that a vector field might have in reference to line integrals, surface independence is a characteristic that a vector field may have in reference to fluxes. Okay. All right, so highly expected by the analogy, anyway, as far as the analogy goes. So here's the picture of what surface independence looks like. So again, let me repeat. Having two surfaces, these are oriented surfaces now, so let me draw the orientations on here. Having two surfaces that have the same boundary curve. Now, you might already be uncomfortable with what I've done here because didn't I draw those orientations kind of opposite way? Aren't they supposed to have the same orientation? And keep in mind, there's two different ways that you might conceivably persuade yourself are reasonable to compare orientations on different surfaces. The real answer, of course, is you can't compare orientations on different surfaces. They're different surfaces. Right? There's two orientations on a given surface, but if you have two different surfaces, I don't even know what you're talking about. Okay. So anyway, thought of as part of the boundary of this solid, these two orientations are opposite. One's inward, one's outward. Right? But thought of in terms of what orientations do they induce on their boundaries, notice both of these induce the same orientation on that shared boundary. And you just got to play the swirl game, right? Think, thumb, fingers, and think about how swirls sideswipe. And these two orientations give the same orientation on that belt. Okay, all right. So hope that sounds familiar. We had a similar sort of one dimension lower conversation when we were talking about orientations, when we were talking about path independence. So same kind of deal. Okay. All right. So, how could it be that a vector field could possibly be surface independent? There's so many different surfaces that have the same boundary. There are these two that we drew here. We drew that one and this one. But my gosh, there's one. Right? You can imagine some sort of highly wobbly surface up there that has that same boundary curve. How could all of these surfaces give you the same flux? Seems implausible until you notice that Stokes' theorem actually gives us a nice example of a huge category of vector fields that have this property. And notice, here's what the Stokes' curl theorem says. Let's look at that surface, S1. Right? It says that the flux, now I'm going to use as my vector field, I'm going to use a curl field. Go by and talk about the diagram in a minute, but let's just take a look at a curl field. Flux of that curl through that surface is, according to Stokes' theorem, a line integral on this shared boundary curve. Right, now let's consider this this other surface here. That other surface, S2. What does Stokes' curl theorem say about this? Now, same vector field. Same, we're looking at the, some curl field, curl of some vector field F. Stokes' theorem says the same thing about that one. Stokes' curl theorem says, well, it's the line integral around that same shared boundary curve. So you get the same answer. These two different fluxes will always equal to each other because they're always equal to this shared line integral. Okay, so that's a picture to digest. Now I want to go back to the diagram real quick, and let's talk it through. Okay, path independence is a vector field that has the feature that whenever you have two curves with the same shared boundary points, that a line integral, the line integral on those two curves will always be the same. And what we've just seen, or what we saw a minute ago, is that gradients always have that feature. Right? If a vector field is a gradient, then it is path independent. Now again, that's old news. I reminded you of it recently, but that's old news. Well, this argument that we just made is morally equivalent to this. Surface independence, we've already talked through how that picture is. The little green diagram chase of what surface independence means looks the same. And notice, following the pattern, you would kind of expect for curls to have that feature. After all, gradients had that feature for path independence, so shouldn't curls have that feature for surface independence? Just seems kind of plausible. That doesn't prove anything, of course, right? But seems like something worth checking. By the way, let me remind you further, thinking back to path independence, how was it that we argued? What was the case that we made to demonstrate that gradients are always path independent? Well, it was the fundamental theorem of line integrals. The fundamental theorem of line integrals proved it for us. Well, again, the pattern continues. What allows us to conclude that curls are surface independent? Well, as expected, per the pattern, Stokes' curl theorem. And that's exactly what we just talked through here. So I think it's a really interesting how, again, the analogy is crazy strong. Right? So that's nice. Okay. Back to the diagram. Let's talk again about, what do we expect? We're going to figure out what we expect based on looking at, what happened in the previous context, and let's kind of extrapolate by, again, the pattern of the diagram. What else do we know about path-independent fields? Well, we did some arguments and showed that every path-independent field, every vector field that is a gradient, its curl is 0. Okay. In fact, that was right here, just as a quick reminder. Right? It's a gradient. Curl is 0. If curl is equal to 0, it's a gradient. Right? That's an argument from last time. Okay. Well, again, that being the pattern, what do we expect to hold? What else can we say about surface independent fields now? Well, again, if I want to take this idea, and see what it looks like one dimension up. And again, this doesn't prove anything, but you would kind of suspect, based on the pattern, that every surface independent field, namely every vector field that is a curl of something, you'd kind of expect that the divergence would be 0. And again, just following the patterns. Again, it doesn't prove anything, but man, if patterns hold, then this kind of ought to be true. So let's think through, can we draw that conclusion? By the way, how are we going to go about doing this? Well, again, we're just going to kind of follow the pattern. So let's see, let me go back down here to it. So here we go. I'm going to, for analogy purposes, shrink this down. We're going to draw through an argument here's our new picture, right? We're thinking about two surfaces with a shared boundary curve. This is highly analogous to over here we had two curves with the same boundary points. Right? We argued previously that when you have two curves with the same boundary points, that, and by the way, all sort of geometric, oddities ignored because I claim they can be dealt with, and let's not worry about it. It's distraction. Such two curves will, between the two of them, be the boundary of a surface. Likewise, two surfaces with the same boundary curve between the two of them should be the boundary of a solid. And again, you got to worry about orientation. Same way over here, we had to worry about orientations, and one's going kind of the right way and one's going kind of the wrong way, depending on how you want to think about it in some sort of a sloppy sense. There's that minus sign that we talked about on the left, and likewise, there is a minus sign, analogous minus sign over there on the right. You just got to think through the orientations, and that's just how it ends up being. Okay. All right. So previously we talked about how Stokes' curl theorem applied to this scenario gives us what we need. We're going to then, by analogy, following the pattern, we're going to apply Gauss' divergence theorem. All right. We're going to apply Gauss' divergence theorem to this scenario, and let's just see what we get. And now, just for visual purposes, let me enlarge this a little bit. So looking at this story here. Here's what Gauss' divergence theorem says. What happens if the divergence is 0? Well, if the divergence is 0, that means this triple integral is 0. That means this difference is 0. Sound familiar? That means that these two fluxes must be equal to each other. This has got to apply no matter what these two surfaces are with a shared boundary curve. Therefore, this vector field is surface independent, and as previously discussed, is a curl. Right, and you can turn the argument around. If you know that your vector field is a curl, well, if it's a curl, then it's surface independent, which means these two fluxes are equal. Which means that this difference is 0, which means that this triple integral is 0. Hang on, if you have a expression, a triple integral that's always 0, no matter what the domain is? What? How could a triple integral always be 0 no matter what the domain is? The integrand must also be 0. And so divergence is 0. And so again, just like previously, analogous to the previous discussion about path independence, whenever the divergence is 0, it's a curl of something. Whenever a vector field is a curl of something, divergence is 0. So, really nice little extension of analogy and connection between these different operators. Okay, lot to digest there. I'm a big believer in the pattern and the analogies, and so I hope you will take some time and look not only at this picture and this argument, right, but look back at that previous page showing on the left side of the screen there, and notice the analogy, right? Notice how everything that we're doing here in regard to surface independence, we kind of already made analogous arguments in the context of path independence. It's the same idea, one dimension up, one dimension to the right on the diagram. Okay. All right. Right. So let's see how we can use this. Show you an example. Suppose I want to compute this flux. Right. So I've got a surface given. It's kind of a weird defined surface. It's okay, I've got this elliptical paraboloid. You see the elliptical paraboloid there? I want to look at the part of the elliptical paraboloid that's above the xy plane. So it's kind of an upside down bowl kind of a surface. There's my surface. My integrand is that vector field. Let's compute the flux. And let's think about our options, by the way. How do we compute fluxes? You've got options. One option is that you can use the pullback, plug and chug, from the parameterization. You can parameterize this. Not that bad, right? And do the whole pullback, capital N is XU cross XV, that whole thing. It's an option. It's tedious. It's an option. Sometimes you can use Stokes' theorem to compute fluxes, right? Reminder, Stokes' theorem. Let me clean up my mess here. Stokes' theorem relates a line integral to a flux. And so we might be able to use Stokes' curl theorem to take this thing that we're interested in, turn it into a line integral. So, it's an option. It's on the table. By the way, just FYI, very often, not a good option. The reason this is not a good option is that if you know a vector field, and if you would like to turn the flux question into a line integral question, notice you're going to have to figure out what its anti-curl is. And you may have noticed I did not give you any methods for finding anti-curls, and that's because it's hard. It's not something that you can usually do. So very often it's just not a good solution. Side note, sometimes the anti-curl may be in a sneaky way given to you. So be on the lookout for inadvertent, hidden freebies, free anti-curls. If there is a free anti-curl, then of course you can use Stokes' curl theorem. Totally fine. Of course, another thing you could do with a flux is you could try to use Gauss' divergence theorem and turn that flux integral into a triple integral. Another option. But again, that only works sometimes, and the catch is that your surface needs to be a boundary of something. You need for your surface to have an anti-boundary solid, right? And now let's look back at our question here. Our surface, this surface here, which I guess I have a picture of. Here it is. Here's our surface. There's that paraboloid. We're looking at the part of the paraboloid above the xy plane. It's not a boundary of anything. There is no anti-boundary. You cannot use the divergence theorem here. A lot of students get uncomfortable with my assertion that this is not a boundary. You gotta make sure to interpret very whoops, I hit the wrong button. I wanted orange. There we go. You've got to interpret very carefully the statement of the question, and in particular, what is this surface? Specifically, we're looking for a part of the paraboloid. Which part of the paraboloid are we looking for? Well, just the part that's above the xy plane. Yeah, sure. This does not say attach to the paraboloid the part of the xy plane that cuts it off at the bottom. It's just not what the question says, right? Everything that's written in the statement of the question, we're looking for part of the paraboloid, and so this surface is just, it's just paraboloid. This is an upside down bowl. This surface does not include a sort of a bottom, saran wrap holding the cereal in. Right? There is no saran wrap on this upside down cereal bowl. It's just an upside down cereal bowl. How are we doing? Is everybody on board? Okay, so be real careful about that. Okay. So we've got three different options for how to compute this flux. We don't really like any of them. Brute force is always, come on, that's always plan B, right? Don't just default brute force things. Your life's going to be super, super difficult if you do that. Anti-curls are hard. We don't really know how to do that. This isn't a boundary surface, so I can't really use either of those theorems. But what I can do is use surface independence. And so recall, surface independence, this feature of surface independence says, let's go back up here. If you have a surface independent field, you're given some surface. Maybe you don't like that surface. Okay. Switch to a new surface that you do like. It's not a problem. That's fine. Pick yourself a better surface. Just make sure it's got the same boundary curve. Now that's strict, right? That's a big deal. Got to keep that boundary curve unchanged. But other than that, change any surface you want. That might make your life easier. It's a very nice feature to have. And we know from this discussion that we can conclude surface independence simply by computing the divergence and confirming that we get 0. This is easy algebra. Computing the divergence, no problem. So compute up that divergence. If you get 0, sweet. We have surface independence and we can change the surface any way we want. Preserving the boundary, of course. Okay. All right. So let's get back to it. We've got this vector field given. Take this vector field, compute its divergence. You get 0. That's an easy calculation, by the way. I mean, not only is it 0, all three of the terms are 0. Sometimes it's an easy... Casual inspection, right? There's no x's in here. The x partial is obviously 0. There's no y's in here. The y partial is obviously 0. There's no z's in there. The z partial is obviously 0. The divergence is clearly 0. So, therefore, surface independent. Therefore, I can take this surface through which I was asked to compute the flux, and I can say phooey on that surface. That's all curved and parabolic and quadratic and, right? That's suboptimal. I like, instead, this nice flat surface down here. I like that flat surface. It's got the same boundary curve. Right? Namely, I can just look at, where does this yellow surface, where is it cut? Well, it's cut in the XY plane, so just look at the part inside the XY plane with that same boundary curve. And now that we've gotten rid of that ugly initial surface, now we have a very different problem. We're computing a flux through now a nice flat surface. And you've got options on how to go about doing this. I like to point out that with this nice flat surface, you can write down the normal vector pretty easily. Think about orientations. The normal vector is straight up. By the way, that's an exercise. Think through the orientations. Think about what's the induced orientation on the boundary curve, and then what of your options on your new surface induces the same orientation on the boundary curve. Having changed the surface, easy normal vector, this dot product then becomes really easy to do. It's just x, y, and symmetry argument. That integral 0 by symmetry, easy symmetry argument. So, again, real quick, right? We just cut the calculations way, way, way down by making a surface independence argument. Everybody okay? Happy? Okay. All right. So, let's see. Before I go on, I want to say a couple of quick things. First, another way to think about the orientations. I'm going to zoom for effect here. Let's see. Yeah, I can do that. There we go. So let's talk about this surface. We had this initial surface given to us, oriented, loosely speaking, upward. Okay. We had this new surface down here, oriented, you might say, loosely speaking, actually less loosely, but still upward. And how do you get from the one to the other? Well, what we're supposed to do is go through and think about how each of them induces the same orientation on the boundary. Right? Make sure that they both go either both counterclockwise, as in this case, or if one's clockwise, then they need to both be clockwise, but they have to agree. Here's another thing you can do. This works sometimes, not always, but very often. You can think about just as sort of slowly and continuously deforming the one surface into the other surface. So think about what would happen if you have, here's my paraboloid, right? Hand gesture. And what would happen if you were to just kind of slowly flatten that out, right? And then think about the normal vector. Here's your normal vector for that paraboloid pointing upward, right? And as that slowly presses down, well, the result is continuously deforming. The result is upward. And you can just see it in that deforming process. Right? So that will work in any case where you can continuously deform one of the surfaces into the other surface. So I think that's highly satisfying. This kind of up-ish, you just see that sort of continuously turning into that one. So feel free to think of it that way instead. Okay. The other thing I want to talk about is why do we care? Let's talk about path independence. Path independence is a computational tool. You turn one line integral into a different line integral. Surface independence is too. The thing about it is, path independence is a computational tool in a context where I already have a really good computational tool. We made this observation at the time. Path independence only applies when you're talking about gradient vectors. If it's a gradient vector, you can find the anti-gradient. You can use the fundamental theorem of line integrals. So, path independence is it's a hammer in context where you already own a hammer, right? It's a second hammer. So, I mean, how valuable is it to have two hammers? I guess if you're going to go two-fisted with the hammering, maybe, right? But it's rare, right, that you need a second hammer. So, as a computational tool, path independence, whatever. Is that true for surface independence? Not really, right? Let's go back to the diagram. Let's see. In fact, let me go forward. I think I have it closer. Oh, gosh, where are my diagrams? Here you go. I'm in the wrong, sorry. Here we go. Path independence in R3, you're talking about line integrals over curves, and path independence is simultaneously with there being an anti-gradient, and you can use fundamental theorem. And we know how to find anti-gradients. We can do that. We have a method for finding anti-gradients. So that's the hammer versus hammer argument against path independence. What about surface independence? Well, okay, analogy, surface independence is simultaneously with it being a curl. The problem is, even though there is an anti-curl, I don't know how to find it. More to the point, you don't know how to find it. Right? Which means you can't use Stokes' curl theorem. Right? So, surface independence is a screwdriver, but it's your only screwdriver. In effect, right? I mean, technically there's a screwdriver, but it's inaccessible. You own the screwdriver, but it's on top of Mount Everest, and so do you really own it anymore? You know what I mean? So as a computational tool, sometimes surface independence is your only reasonable option for computation. So I think it's really important for that reason. Okay. Alrighty. So moving along. So let's talk a little bit more about physics. This is not a physics class, so I'm going to go real quick through this, but it's so powerful how these theorems, these vector calculus theorems, how they apply in physics scenarios, especially to electricity and magnetism and gravity. The specific what it is about. One of the neat applications, I'll say, of Stokes' curl theorem, curl in general, to physics concerns current and magnetic fields. Okay, so we're going to entertain a generalization of this idea. A current, as y'all have probably seen it before, is usually contained in a wire, right? Y'all have wires running around all over your house, and there's current flowing in those wires. Right. What you may not know, but if you've had an intro physics class, you do, is that when you have current in a wire, and I've got to get my perspective right here, current in a wire creates a magnetic field that kind of wraps around the wire. That's just the way this is all empirical. The universe seems to be built this way, best we've been able to notice. Why do magnetic fields do that? That's a deep question, philosophy department question, right? I don't know. But they do. We've seen it, and so this is how everything behaves. Okay. Now, so let's generalize the idea of current. Current. Oh, by the way, which way does the current go? Or which way does the magnetic field go? The magnetic field goes. There's a kind of a right-hand rule. They actually call it that. But if the current is going in the direction of your thumb, then the direction that your fingers of your right hand, right hand, sort of curl around. That's the direction that the magnetic field goes around. Okay. So a generalization of current in a wire is just free-flowing current. Free-flowing current, well, it's a flow of a fluid. The fluid just happens to be charged particles. And this is called a current field. It's a flow field. It's a flow of a fluid, right? But since it's a flow of charged particles, moving charged particles, we've already associated the word current. I think it's reasonable. We call this a current field. Okay. Very often, the letter J very often is used for that. By the way, I is very often used for scalar current. J, next letter in the alphabet. Could be worse choices. Okay. So, similar question. Then let's ask the question, okay, fine, we've got a current as a different kind of current, but what do magnetic fields do? I hope it's no surprise. The magnetic field wraps kind of, sort of around, I'm going to try to draw this one being behind there. It kind of wraps around the current field. Okay. All right, so where have we seen a picture like this before? Things kind of, you have with this purple vector field kind of swirling, if you will, kind of swirling around a certain direction, and then there's orange vectors that point in the direction that the purple vectors are swirling around. That's the exact same kind of a picture that we drew when we were talking about curl. And that totally holds here. The curl of the magnetic field, we use B for the magnetic field. The curl of the magnetic field is proportional to the current field. Okay. So, neat fact. Again, this is just how the physical universe is put together. Okay. All right. So I like to point out that what this means is that current fields, the physical universe constructs out of current fields. It constructs the anti-curl for us. Again, the physical universe manufactures the anti. So it was divergence when we were talking about gravity, right? But it's anti-curl as we're talking about electric fields. So, quick argument here. Let's think in terms of what happens if you have a color choices here. What happens if you have a current field? Now, I want to talk about steady state flows. Steady state. By the way, the reality of how E&M works and all these rules about divergence and curl of electric and magnetic fields is actually a little more complicated than we're describing here. You have to make certain assumptions. Here we have to assume a steady state. If there's a non-steady state where the current is in the process of increasing or in the process of decreasing, or if there's charge accumulating in one location of space and there's just an increasing buildup of charges, everything's a little bit different and it's complicated, way beyond what we can do in this course, and we're not going to touch that. We're not going to talk about that. So in order to bring this to relatability, we're going to talk only about steady state flows. And by the way, steady state, if you think about it, steady state means that the divergence would have to be zero. After all, divergence is telling you to what extent is there something happening. Like if there's charged particles diverging away from some area, then they can't just spontaneously generate. You must be losing charged particles from that area, and that would violate the steady state condition. Okay. So if the divergence is zero, you have a steady state flow. Consider a flow of charged particles flowing per your field. Right? Well, those charged particles construct a magnetic field. Again, the physical universe does this for us. No calculation required. It makes a magnetic field, and notice that that magnetic field is the anti-curl. Right, so again, we have this situation where the current physically creates its own anti-curl in this case. Just like mass, by way of its gravitational field, mass generates its own anti-divergence. Current creates its own anti-curl. Yeah, it's very thoughtful and nice of the physical universe to make these physical models for us, right, to help understand these things. So if you want to think about curl, one way to think about curl is the current that creates the whatever magnetic field. Think in terms of magnetic fields, whatever field you're looking at. Okay, all right. I think that's a fun little digression. Let's talk again about Maxwell's equations. Again, if you've had an E&M class, you've probably seen some of these before. If you have not had an E&M class, this is going to be a real big savior for you when you do. This will help you a lot in understanding, getting a physical sort of geometric kind of sense for what Maxwell's equations are really saying. So here's that equation that we just wrote down. The curl of a magnetic field is the current field that created it. Okay. There's another one. And again, this is not a physics class. I'm not going to go off into talking about the physics side of the curl of an electric field, but it happens to be the negative rate of change of a magnetic field. Again, it's empirical. It's weird, but it is. Okay. So we're going to do something totally analogous to what we did before. There's that theorem. There's that theorem again, right? These what we call differential versions of those two of Maxwell's equations. And here we're just going to take a flux of both sides. Free country, right? You can take a flux of both sides of an equation if you'd like. And so having done that, notice then that we're looking at a flux of a curl, and Stokes' curl theorem tells us what you can do with a flux of a curl. A flux of a curl is a line integral. Straight out of the first statement of the theorem, that's what Stokes' theorem says. Yep. What do you do over on this other end? This is just a rewrite. Flux of a magnetic field. We don't think of a magnetic field as being a flow of a fluid, so I can't rewrite what that is in terms of other relatable things. But we give it a name. We just call it phi, right? Phi for flux, and B as a reminder that we're talking about magnetic flux. Over here, on the other hand, it's really easy to talk about flux of a current field. After all, the current field is a flow field. It's literally a vector field representing a flow of a fluid. The fluid just happens to be charged particles, whatever, but it's still a flow of a fluid. And if you were talking about a flux of a flow field, right, what you get, the initial notion of what flux is in the first place is that it's how much of that fluid is passing through at any given point in time. These being charged particles, how many charged particles are moving through a given point at a given time, that is a pre-existing physics notion called current. And again, so we write that with I. All right. So with this argument having been done, note we've showed two new theorems, and I'm going to just for convenience, I'm going to rewrite them like that. And this theorem I'm going to rewrite as well, just for visual convenience like that. We have two different versions of the same theorems. So technically, I guess they're different theorems, right? These are about curls of E and B fields. These are about line integrals of E and B fields and their corresponding fluxes. So they are different, I suppose, but they're morally, the connection between them is Stokes' curl theorem. One is a local differential version, right? The other, two are global integral versions. They involve integrals. Those up there involve derivatives. So we call them two different versions of the same theorems. So, or the same equations. So these are, depending on your choice of preference of order, these are Maxwell's equations numbers 3 and 4. Some people like to order them differently. This, I think, makes sense. Okay. All right. So I think it's good to see that. Again, Stokes' theorem is the thing that makes the key connection here. That's what makes it all possible. Okay. All right. I'm going to skip this next page. We are short on time, and it's not really this is a little bit more in the physics class direction than we really need to go. I think it's nice when we have time to be able to cover this page, but it's not important. You don't need to worry about it. But on the other hand, if you would like to test yourself to see, do you really have a good understanding of how Stokes' theorem, in the form of how it relates to Maxwell's equations, can be used to study magnetic fields, then this is a great little exercise. And all it is, I'm just going to hit the highlights for you, is it says suppose you have a flow of charged particles, namely a current field. If you have a current field, you can talk about the total flux through that surface. And if you know the flux through that surface of the current field, aka if you know the current, then that'll tell you a line integral of the magnetic field. That tells you what the line integral of this magnetic field is going around the outside here. And in this case, as I have things set up, knowing that line integral actually allows you to come to understand the B field itself. But that's sort of the symmetries and peculiarities of this particular setup. So anyway, it's just an immediate application of the theorems on the equations on the previous page. So give it a look if you're interested, but not really quite required. Okay. All right. We are, believe it or not, kind of done with Stokes' curl theorem. We are kind of done in a way with with chapter 15. Kinda. And we've covered all the theorems in chapter 15. I've got a bunch of pages of notes left to talk about, though. There's so much that happens in chapter 15. There's a lot to digest, and I think it's nice to give some summary discussions and to talk about the analogies a little bit more, and then do some examples. So I'm going to show you, I have 6, I think, pretty good prepared examples of how do you use all these theorems in practice, day in and day out, to actually compute line integrals and surface integrals. All right, so it'll be some good exercise. We're not going to finish this today by quite a bit, but we'll finish it up on Monday. Okay. So first thing, I want to talk about these theorems. As you'll recall, I'm a big fan of this idea of thinking of all of these theorems as involving integrals of densities. We're looking at accumulating quantities. Accumulating quantities add up as integrals. The integrand is always a density. That's what it means for something to accumulate, kind of, right? And that those densities are algebraically recognizable in these theorems. So let's walk through, instead of going through one at a time, let me walk through the points, doing all the theorems sort of simultaneously as we go through. Okay, so here are the 5 big theorems. Right, fundamental theorem of calculus, of course, is old news. The fundamental theorem of line integrals is arguably kind of 2 theorems, because there's the 2-dimensional version and the 3-dimensional version. So if you want to think of that as a total of 6 theorems, whatever. Green's theorem, Gauss's theorem, Stokes' theorem. Okay. In all of those theorems, we are computing an accumulating quantity. In each one, it's a different accumulating quantity, but in all of these theorems, there's something that's accumulating. Make sure you understand. I think it's really important, just for intuitive reasons, to have a sense of how each of these is computing an accumulation. Right? So with the fundamental theorem of calculus and the fundamental theorem of line integrals, we're looking at change. There's some function, and we're trying to compute f of b minus f of a. That's change. And we argued how change accumulates over the curves. with Green's theorem and Stokes' theorem. Look back at those theorems. You're computing circulations. We've got some vector field we're looking at how the vector field is flowing along a curve that starts and ends at the same point. That is a measure of how much that vector field is representing a fluid that's kind of going around with that curve. That, of course, goes kind of sort of in a circle, being as it starts and ends at the same point, and thus the term circulation. Accumulating quantity. Accumulating for sort of geometrically different reasons, but still accumulating. Gauss's theorem is doesn't have a friend in this discussion, but it's still computing an accumulating quantity. It's the only one that's computing boundary flux as an accumulating quantity. Okay, so these are accumulating quantities. You compute accumulating quantities with integrals. All of these accumulating quantities are computed with integrals. Integrals of, a corresponding notion of density, right? Integrals of, we talked about all these different notions of densities. No surprise, the theorems where you're computing change, we interpret those as change density. The theorems where you're computing circulation, we interpret it as circulation density. But in all cases, it's a density. In the example where the theorem where we're computing flux, boundary flux, but still, makes sense to call it flux density. Very common terminology, very geometrically natural and important. So again, notice the very strong patterns: accumulating quantities appropriate to the circumstance, computed as integrals of corresponding densities, appropriate to the quantity that's actually accumulating. All of the theorems. Okay. And then, of course, there's the little asterisk with the orientations, right? So Stokes' curl theorem and in fundamental theorem of line integrals, we've got to interpret those as oriented densities. After all, they are vectors. Right? They point in directions. Those directions mean something. With these others, they're scalars. There is no direction. There's no sort of oriented feature to the densities, but with the oriented ones there is. Okay. Alrighty. Okay. Another. I want to point out the pattern. We've already done some of this, but let me do a little bit more. There are special vector fields that I want to talk about in R2. Special vector fields go by many names. These vector fields that I want to talk about. These special vector fields. On the one hand, they are gradients. In other words, they're vector fields for which you can use the fundamental theorem of line integrals, if you like. We've also seen that they are path independent, which I like to represent on the diagram like this. Right? Path independent. Simultaneous. Irregularity issues aside. They're, ignoring that. Every gradient is path independent. Every path independent is a gradient. And furthermore, they all have the feature as well that Green's operator is 0. And so let's see how we can write these all down. Oh, let's see. Do these fit? Okay. Right. So being a gradient, being path independent, Green's operator is 0, and by the way, keep in mind this term irrotational, and don't forget what Green's operator is. Green's operator is circulation densities. It's a way of saying how much of this kind of swirling fluid do we have going on, and if Green's operator is 0, well, that means there's none of this going on, and that means that the fluid is not rotating, and thus the word irrotational. So another word that's out there, you will see. So we've talked about these vector fields previously. There are, again, any vector field, regularity aside, that has any one of these properties also has the other two. And it's very computationally convenient. And now there's 2 more pages here that are the exact same things. So super quick. Any vector field that is a gradient is also path independent. Also has the feature that curl is equal to 0, and we write it down slightly differently when we're talking about R3, but it's morally the same. And furthermore, here it is. There are certain vector fields that are curls and simultaneously surface independent, and simultaneously their divergence is equal to 0. Okay. And I have those summarized down here. So keep in mind, gradient, irrotational, path independent all mean the same thing in R3. And for fluxes, being a curl is the same as being surface independent, is the same as the divergence being 0, and there's a physical interpretation here that people will talk about steady state fluid flows or incompressible fluids, and divergence equaling 0 is suggestive of that. Okay. All right, so those are the special ones, and so make sure to keep in mind. Now, I'm not saying all vector fields have these properties. No, of course not. But it's nice that those that do have all of the others as well. Okay, so next time we will talk about strategies for computing line integrals and surface integrals, and do a bunch of examples, and then we're gonna pretty soon here have to start on optimization back in chapter 13. So we'll probably do that. We'll probably touch on that on Monday. Okay, see y'all later. Have a good weekend. And for some of you, happy Thanksgiving.